So I was asked to talk about inflation and particularly how we test it. And so this is something that I found in my I don't know, list of presentations, and apparently at one point I made this picture, which was, I guess, applicable to this presentation. So to get everyone on the same page, of course, I think that many of you here might be familiar with the cosmic expansion, but still relevant to give some context, especially when we relate what we think happened in the early universe to what we observe today. So the main topic of this workshop today, of course, is to see whether we can learn something about inflation or alternatives. And the way we think we can do that, of course, from an observational point of view, is that what we think happened in the early universe must be causally connected to something that happened late time. Specifically, what we try to do is we try to measure statistical properties. Right? So we're looking at statistical properties, for example, in the distribution of galaxies, or statistical properties of these fluctuations in the radic afterglow of the Big Bang that Marieke just introduced. And so by measuring these statistical properties and theoretically, I guess, to some degree, relating them to what happened in the early universe, we try to infer the physical laws of nature that governed the early expansion or alternatives. So just to set that stage. Now, in terms of what we can observe, of course, there's a whole bunch of things. So I already mentioned the cosmic magnetic background, and you can actually also observe the distribution of galaxies. And then there's this period roughly between redshift of 1100 and 200, where there's very few traces. In principle, if there's something that produces gravitational waves, it might still be possible to get some information from that part of the universe. But in principle, it's quite dark. But from redshift 200 to today, you can actually observe pretty much the entire universe, which is something that I'll discuss also in this talk. Now, as I mentioned statistics, the reason why we're looking at statistics is that we don't have that much absolute information. And also it turns out that absolute information doesn't really guide us in what happens during inflation or in the early universe in general. And so just to think, let's say the average temperature of the CMB that Marieke mentioned, that doesn't really contain that much information, right? So that's why we rely on these statistical properties. Now, if we think about statistics, if we think about this in terms of one-dimensional distribution, you can think about these as moments of some distribution. And you could, given that you typically remove the mean, the statistical properties that you can think of are the variance, and then higher order moments such as the skewness and kurtosis. And at the field level, because we're working with fields, right, we're working with quantities that depend both on space and time. These kind of statistical properties are promoted to so-called endpoint correlators, which in Fourier space are then denoted as n-1 spectra for some reason. But that's just to give you an idea why that's what we're doing. Now, I think another important part here is that if indeed these fluctuations that we observe, for example, in the distribution of galaxies or in the CMB, they're Gaussian, then the entire information we can ever hope to learn from this field is by looking at this variance, the power spectrum. And so if it turns out that the fluctuations in the early universe were Gaussian, then all the information that we've already measured, all the information that's present in that field in some sense. So that would be bad, yeah? So I'm not sure how many people are familiar with how we tend to measure things in the CMB, but here's a very quick cartoon. So we tend to use this multiple projection, that's something that you might have seen, I don't know, in your quantum mechanics course or just generally. So that's just one way to decompose the sphere. And we're measuring correlation functions, and that turn into these power spectra. So we're looking at the power as a function of scale by summing all these maps. And we can do that, for example, for the 2-point correlation function, but we can also do that for the 3-point correlation function in the CMB, right? And this, of course, this would be 0 if this map is Gaussian. And then we only have to worry about this 2-point correlation function. So that's roughly how it works. Now, and what have we measured so far? This is a measurement done by Planck, so these are real data points. And we can put our theory curve right through those data points. So we have a very good understanding of exactly why the power spectrum looks this way. And what's quite remarkable is that we can also measure not only the temperature, but we can also measure the polarization of these fluctuations. And these are the measurements. And then given the theory that we, or given the theory curve that we actually deduce from the temperature measurements, we can predict what this polarization signal looks like, right? And that's, I think, really showcasing how well we understand the CMB at this point, right? The fact that we can predict exactly what the polarization signal looks like, given the measurement that we make in temperature. Now, the main point here is that the peak structure here tells us something about cosmology. So the way we infer about cosmological parameters is by looking at the peak structure here. And what we've learned from that analysis is that we have this very nice and elegant model of the universe known as lambda CDM, where lambda, as you might know, stands for the cosmological constant, and cold dark matter, or CDM stands for cold dark matter. It's governed basically by Einstein gravity. So this is the Einstein equations that Marieke already introduced. And I think important for this story is that for the Gaussian universe, all we need is this spectrum of initial fluctuations. And there's only 2 degrees of freedom here, which is the amplitude of that spectrum and the scale of that. Yeah. And that's related to the 2-point correlation function of beta, where beta is the curvature perturbations in the early universe. So inside the Einstein equations, because we can measure the expansion, we can learn something about the density, and we can learn something about the initial conditions, right? So in total, there's only 6 degrees of freedom. So on top of these, we have the expansion, and we also have the optical depth through reionization. And so that's all we need to inject. Now, in principle, there are additional hidden degrees of freedom. So we say there's only 6 degrees of freedom, but we do set some things that we've measured through other ways. For example, the helium fraction is fixed, but in principle, you can also vary that if you want. Okay, so that's the first story. So why inflation? Now I want to kind of quickly go through because Marieke already mentioned some of these things, but what I call old conundrums, or conundra, I think it is actually. But I realized that and I forgot to change it. But the main point that Marieke already mentioned is that the universe looks very homogeneous on scales that are beyond the causal horizon, and I can show that maybe that's in a little bit more depth later on. So that's the horizon problem, and the fact that the universe is so close to flat. Well, that's an unstable solution. So if you go back in time with this, and you have some deviation from flatness now, then that deviation will become larger in the past, right? So you have to be very, or it has to be even smaller in the past. So that's kind of a fine-tuning problem. Now, we could also think about new conundra. So one of them is the fact that we have this positive correlation between temperature and polarization modes on very large scales. And so this is sometimes referred to as phase coherence problem. And that's new in the sense that these were proposed when we didn't think about fluctuations. And these are really derived from the fact that we do measure fluctuations. And of course, as Marieke was already mentioning, inflation predicts these fluctuations, but then after measuring them, it seems that we have some issue if we do not have something like inflation. Another thing that is also evident from the observation of these fluctuations is that they appear scale invariant, or very close to scale invariant. Okay, so just in kind of a picture, this is the spectrum, this correlation function. Now we use the letter D instead of L times L plus 1 times C over 2 pi, but that's just a small detail. But the main point is on very large scales, you have this positive correlation. And you can think about these E-mode fluctuations as velocity fluctuations. And so if you work out a very simple model of what this correlation function should look like, then if you take random phases, it turns out that you expect this correlation to be exactly 0 on these scales. So these scales are, in some sense, primordial. They only entered our horizon after recombination, and so they're really truly what we think primordial without any further processing or really limited processing. So the fact that it's positive is puzzling. Another part here is that okay, we see all these bumps and humps in the spectrum, but again, on very large scales, it's pretty much primordial. And if we actually try to measure these initial conditions by varying this parameter ns, which tells us something about the scale invariance, then this thing looks very much scale invariant, right? So I mean, there's a slight tilt, but it's very close to scale invariant. Okay. So that's because we can literally just measure the spectrum on large scales, and that is almost flat. So it turns out, as again, to reiterate what Marika said, that if you have something like inflation, so the horizon problem can be solved if you have the derivative of the scale parameter to be larger than 0, as well as the derivative. Flatness can also be solved by the same mechanism. And of course, both of these basically suggest that something like inflation must have happened, right? Now, of course, in many of these cases, you could also do both of them negative. Yeah, so that's something that people have, of course, also proposed to be something like a crunch or like a cyclic model, right? A bounce. The new conundrums, the phase coherence problem actually also, if you work this out, it also suggests exactly it's A dot and A double dot can be larger than 0. And scale invariance you can have when you have a space-time that's maximally symmetric, like a sitter. And in that case, you find that you can actually produce the right symmetries that will lead to a scale invariant spectrum. And of course, then it turns out that the sitter also is kind of like inflation, right? So in that sense, it's all one big circle. So inflation solves these background problems, but it also generates fluctuations for free. And it actually has the correct spectrum if it's constrained to solving the background problems. So if you set it to say, oh, it has to solve these background problems, it also produces exactly the spectrum that that we observe. So in that sense, it's predictive and it fits our data quite nicely. Now that's all nice, and so that's why a lot of people are a fan of inflation. And so please raise your hand if you're not, we can discuss. But of course, there's only limited number of parameters that we can try and fit, right? So in our model, we only have AS and NS, and that's problematic, right? Because now it becomes more like a question: can we even test inflation beyond these very minimal numbers of parameters? And so, in principle, even though you might think it's part of lambda CDM, but R is actually an additional degree of freedom that is not part of lambda CDM. And so at the Gaussian level, if you measure gravitational waves in the B mode spectrum, for example, of the CB, then that would be an additional way of constraining inflationary models. So that's, of course, what people have done. What am I? Yes, sorry. So I'm just wondering if I have the same slides, but I don't. So these conundra, they demand this these two things for A, and it's not really possible with ordinary stuff. You need a light scalar field, or in the example of Marika, a Higgs field might be possible, but then you still have to modify a few things. And so it turns out that basically comes down to this energy condition where you have a kinetic energy that's much smaller than the potential energy, and that's why we typically refer to this as slow roll, right? And then we define slow roll parameters associated with this. Now, I do want to mention that something that I think maybe is more something that people are thinking about now, the way people think about inflation, is that usually we do write down these potentials and we think, oh, we observe everything that happens in the bulk of what happened during inflation. But of course, what we are seeing is something that is imprinted at the end of inflation. So we're really only observing something at the boundary. So that's maybe illustrated a little bit in this figure, where the production of these particles, as Marika mentioned, is shown here, and they're produced at different times during inflation, and that leads to slightly different end times of inflation, which results in a spectrum of temperature or galaxy distribution, right? And so they don't annihilate and they are correlated. So that's roughly what happens at the Gaussian level. And from that, if we measure these two parameters R and NF, so assuming that AF maybe is less relevant, but R and NS are really the key parameters to discriminate between different inflationary models. So these are measurements done with the BICEP-Keck telescope at the South Pole, measuring the extent of the scalar ratio. And what is plotted on this these constraints are different models of inflation. So, for example, different models of power law inflation, depending on the shape of the potential being either convex or concave. You already see that several of these power law models are excluded, right? So that gives you a handle. So I think this is really one of the favorite plots that we have in inflationary theory, because we can put our PET model on this plot and say, oh, is it excluded or not? Yeah, so that's roughly what we can do now with Gaussian measurements. So for testing inflation, these are all very powerful constraints, and they all are so far to some degree consistent with inflationary physics. There's nothing really telling us that this is not inflation. Nothing's telling, oh, if I'm measuring this value of, or if R is below this value, which is basically what we have now, and it has this value, it has to be something else. That's not at all what we can learn from current measurements. And it's even, I would say, it's also a little problematic if we do not measure R. And of course, this is in principle possible, right? There's maybe a gravitational floor, but it's really, really low. I'm not sure what it is, like 10 to the minus 58 or something like that from BBM. It's like this very low number. So I think that means that it could never be observed. So if that happens, right, we will not learn that much more about inflation. But the main point is that if indeed these fluctuations are Gaussian, that is the case. And then all the information is in the power spectrum. But if the fluctuations are non-Gaussian, then all moments are excited. Yeah, as I mentioned before, you could have students and kurtosis. And to some degree, what we're trying to extract, if you want to measure these the properties, the statistical properties of the initial field, is some distribution function or probability function P of zeta, where zeta are your curvature perturbations related to perturbations in the inflaton field. And so we can reconstruct this probability distribution in principle moment by moment. And then, as said, at the Fourier level, the moments are denoted as bispectrum and trispectrum, etc. Right? And so collectively, all these type of different spectra are labeled as non-Gaussianity. So that will be the remainder of this talk. I'll talk about primordial non-Gaussianity. So the way to think about that at the level of the bispectrum, you could have a situation where you have some fluctuation popping up, a particle being produced, and that could be coupled to some mediator field sigma, and then later on, two other particles that are decay, for example, from this mediator field are produced, and that means later on they are actually correlated. So these type of interactions between some mediator particle and the inflaton, in this case, would lead to bispectra that have this very particular shape, right? So if you have something that happens very early and then some other production very late on, much later, correlated, that leads to these kind of local type bispectra. If you have some interaction, like a 3-point interaction, then of the inflaton field, then you can get a spectra that are what are called equilateral. So they have roughly the same wavelengths, right, in this triangle. So that's roughly what you should think about this. And so again, really, we can't observe what happens exactly in here. We observe what happens at the boundary. So it turns out for the simplest models of inflation, so for these very, the most naive model of inflation, we do not expect large non-Gaussianities, but there's a whole bucket list of things that could happen to generate these large non-Gaussianities. So if you have additional fields, if you have strong self interactions, if you have non-standard vacuum, if you have heavy particles, and that's nowadays referred to as a cosmological collider, if you have non-attractor dynamics, so inflation is an attractor solution, but if it's non-attractor, you can have large non-Gaussianities. You have classical production, so if you think about all these fluctuations could be quantum, but in principle, classical production could lead to large Gaussianities, magnetic fields, strings, I don't know, you name it. And then, of course, if you think that inflation didn't happen, but something else, in principle, alternative models could be deduced from specific features in these higher order correlation functions. And anything that you can come up with, I guess. So this is roughly the only equation I have in my entire talk. So this would be the bispectrum, right? So the correlation function of three perturbations. It has a conservation of momenta, and then it's proportional to AS squared. And then for a scale invariant spectrum has dependence that goes like 1 over the modulus of the momenta to the power 6. But what is relevant here is this overall amplitude FNL with some label that we call phi or whatever, and then there's the associated shape. And you already see that this has a lot more constraining power than just the power spectrum, because that only depends on these 2 degrees of freedom, AS and NS. But here you have an entire family of shapes that you can think of, right? Which all could have different amplitudes. So you have much more freedom. So here you can do kind of simple spectrography where you look at the dependence, the scale dependence of this shape, where you set 2 of the momenta to 1, and you take the ratio of the other 2. And you look in so-called equilateral limits, where you set all the momenta roughly to the same amplitude, or you take this so-called soft limit or squeeze limit, where the triangles look like this. And you see that different shapes, so these are the types, equilateral, orthogonal, total, and then if you have some exchange particle, some mediator particle, you see that they all behave differently as a function of scale. So if you could measure this, if you could measure these shapes, you already learn a lot about the dynamics, right? And potentially about new particles that were present during inflation. So that's the idea, the goal to measure something like this in the data. And given these shapes, of course, then we have to put some numbers on what we think are relevant numbers in inflation. And so we set out and made this table about 8 years ago with a group of people. And this is very, I'd say qualitatively, even though we put some quantities here, but obviously it could also be 3. Yeah, the number could be 3, it could be 2, it could be a half. But roughly speaking, this is what we think are relevant numbers. And by setting these numbers, depending on these types of non-Gaussianities that you have, if you find local non-Gaussianities to be larger than 1, it will most likely be multi-field. Certainly it will not be single field inflation. And also if these equilateral or orthogonal shapes are larger than 1, then the fields must be non-weakly interacting. So that's very kind of qualitatively distinction between different models of inflation by looking at the numbers that you would get from observations. So now the question is, how do we detect these things in real data? That's a lot harder. So this is the CMB, simulated image. I can crank up the value of FNL, and if I do that, you'll see that only maybe if FNL is about 1,000, you really start to see it by eye. If it's anywhere near 1, which is where we're looking or searching for, you can hardly see it in the data, right? It's very hard to see. Okay, so now I have a bunch of figures. Let me just try and carefully explain them. So what we're showing here is signal noise squared, in this case, as a function of this multiple parameter that we use to show the angular scale on the sky. So that means that higher multiple means that you're looking at higher resolution. You see, as you go to higher resolution, because of statistical isotropy, you increase your signal noise. And the main point is that we have 3 lines. We have temperature in blue, E-mode polarization in orange, and then the combined signal to noise in green. And if I just take a random number, right, so we assume for this kind of forecast that FNL is 1 of all these different shapes, local, equilateral, orthogonal, and you see that to reach, let's say, 1 sigma in the CMB of FNL equals 1 for local, you need this L max of 4,000, and you're like, okay, well, why don't we just look for that in the data? And to reach that value of L max, assuming everything is perfect in this case, it's a kind of perfect measurement. This we can do maybe in, I don't know, let's say 5 to 10 years at best, right? So, and then we have to be very lucky because we're not observing the full sky, and there's noise and there's additional things. that you have to worry about. But for local, who knows? It could happen. For all these other shapes that would define, let's say, whether a field is weakly interacting or not, you can extrapolate this and you would need something like Lmax of 130,000, which is completely out of the question. So you can never measure these types of interactions if you're looking for FNL equals 1 with the CMB. Okay, so that's the method. CMB could maybe reach FNL local of 1, but the other shapes that would tell us something qualitative about the inflation is very hard. Now, another thing to point out is that you see that this has a certain scaling, right? That scaling is very specific, and that's because as you measure higher resolution, because of statistical isotropy, all these modes are independent, right? So the fact that the universe looks the same in every direction means you can sum over smaller and smaller modes, which gives a lot of information. And so what you see here is that for some reason, equilateral and orthogonal, they don't scale as fast as local. And that's due to the fact that the CMB is really not, it is a surface, first of all, it's a two-dimensional surface, but it's also blurry because it's not, not all the temperatures are produced exactly at the same time. So you're looking at a very blurry image of this last scattering, and that actually has a big effect on these type of bispectrum. So that's also makes it kind of annoying if you want to measure these other shapes. So what we have now with Planck is we get an error bar on this value of FNL. Quite remarkably, looking at this, by eye, you think, well, FNL of 1 is hard. It is hard, but roughly our error bar is of the order 10. For local, it's actually a little bit lower. Delta FNL is 5 for Planck, but for equilateral and orthogonal, they're more in the order of 30 to 50. We can still improve these constraints, but as you can see, it's very hard to improve them by a lot. So at best, I would say future measurements like the Science Observatory, which I'm involved in, S4, we can maybe push this down by a factor of 2. That would still be interesting. So let me also say that FNL could be 3. Yeah. So it's not like I say that FNL has to be 1. It's just that some people say, well, you need to put a threshold. The threshold is roughly 1. To reach that, it's hard. Now, I only talk about scalar signals so far, but in principle, if you can imagine that there's interactions also between gravitational waves and scalars, and those can be improved quite a bit simply because we measure these gravitational waves with B modes, with B mode polarization, and that is improving a lot in the future. Oh, oops! Oh, I had this before. So annoying. 1 second. Where was I here? Yeah. Okay, so of course now we can ask, if I had all the money in the world, what should I do? Yeah, and is there anything that could limit our ability to detect these signals? Because I think they're very profound. Yeah, so it's something that really would distinguish between various inflationary models and perhaps alternatives. Now, we even though if we had all the money in the world, we still have to worry about the fact that we only see a finite slice of the universe because we have a cosmological horizon. And there's also only one universe, so we have to deal with cosmic variance. There's information loss, right? There is not all the information that was generated in the early universe is preserved as the universe evolves. Even if it was there, if you don't have anything to observe it, yeah, we cannot measure it. So that's a lack of tracers. If we are behind a curtain, like foregrounds, we cannot observe it either, right? I always say, like, would it be nice if, I don't know, for some reason, our solar system was ejected from the Milky Way? It would be super nice, yeah? It would help us a lot, but that's not the case. Of course, also in terms of technology, as I mentioned, let's say I want to do this equilateral measurement of the bispectrum with CMB. I could do it if I had a lot of money. I just built like, I don't know, a dish of 20 kilometers that we could measure CMB photons. But of course, technologically, it's not feasible, right? So that's systematics. I don't know all my systematics. And another thing called cosmic coincidence discussed. But so I will focus mostly on this, right? So if I only have to worry about this thing, I guess Horizon is folded into this, but these two things, not so much about, well, I'll talk later about information loss as well. Yeah, so mostly about these first three things. So given that you just need more modes, higher resolution, where would you look, right? And Lisa would tell you have to look at large-scale structure. Yes? And I agree to some level. But the main point is I can kind of qualify that or quantify that by looking at the co-moving volume, the total co-moving volume up to last scattering. How much volume is available to even look for that information? And so I can check and compute this. Of course, these numbers depend on cosmology, but roughly 20% is a large-scale structure. So good choice, at least that you work on large-scale structure. Epoch of reionization. So when the first stars started to ionize the universe, 24%. Cosmic dawn, when the first star started to appear, 50%. And then there's this chunk, the dark ages, which is about 30%. And then there's this region, roughly order 10%, where there's basically no tracer unless there's some, I don't know, primordial black holes that emit gravitational waves, right? Okay, so that as a theorist, I'm just going to do the simplest thing. And I say, if I can measure this, are there even enough modes here that I can use? So during this dark age, that's what we did. So the way to measure these modes there, these available fluctuations, relies on measuring 21 centimeter photons. So these are naturally produced because you have hydrogen. The most of the universe consists of hydrogen. Hydrogen consists of a proton and electron. The spins can be aligned or anti-aligned, and the energy difference between those two states is associated with a wavelength of 21 centimeters. Okay? And that can be measured. So the way we measure this is against the CB background, which has a certain temperature, and then we associate this number of states either in the parallel or antiparallel state with the spin temperature, and then there's this optical data. Right? We know all that, and we can measure the brightness temperature, which is the difference between these two, and we see that roughly speaking, so again, this is kind of qualitative behavior. It depends on the ionization model, etc. But roughly it looks like this. You have a deficit with respect to the CMB during the dark ages, a larger deficit during cosmic dawn. Then the universe reionizes, the universe heats up the intergalactic medium, and then you get this positive brightness temperature. And at the very end of reionization, this basically almost goes to zero, but it's still in principle possible to measure this signal there as well. So let's say, again, you're a theorist and you work out what you can do. So instead of showing signal to noise, I show here these error bars, which are just the inverse signal to noise for FNL equals 1. So just think about this. If you want for yourself, you can invert this and take this and square it. But the main point here is that we can look at when you could measure FNL equals 1, and that's quite easy. So before I said L max, here I'm using what's called baseline. The baseline just means that when I measure these kind of fluctuations in the sky, I have to build a device that consists not of a single dish, but of a whole series of dishes, a so-called interferometer. And this interferometer has a certain baseline, which means I have a lot of dishes, and the largest baseline, which is the largest distance between two dishes in my instrument, sets this baseline. So if I can build an instrument with a baseline of, say, 10 kilometers, which is not entirely crazy. We're already building these kind of things on Earth to some degree. Like SKA has a baseline that's larger than 10 kilometers, to give you an idea. It would be possible. For equilateral, you have to build a larger experiment. So again, it shows you that equilateral is just harder to measure. And what you also see is that when you measure these 21 centimeter modes, when you have to choose a frequency resolution, and that frequency resolution roughly has the same effect as the blurring of the CMB we saw before. So you see if you increase that frequency resolution, so you blur more modes, you lose more signal to noise for this equilateral shape. Our local doesn't really care about this effect. So okay, imagine you can build such a device. Now there are all kinds of issues, and if there was like one serious 21 centimeter physicist in this room, they would tell me I was crazy. In fact, it's really hard to measure these modes because our own ionosphere is not transparent to these wavelengths. So I have this rendition. So if we could build something like this, we'd be able to do it, right? So you have to do it on the backside of the moon, and you wonder maybe they were already detecting these long-Gaussian entities with the Death Star. Who knows? That's why they were building it. Why did they destroy it? Who knows? Okay. main point is, okay, yeah, so the main point I want to make is, so even if you don't care about all of this, it turns out there's still something you have to worry about. And what you have to worry about is what's called non-Gaussian covariance. So if you make a measurement, let's say you make a measurement of the mean of a quantity, your error is given by the variance, the square of your expectation value. Yeah. What you have to measure here, when you measure the bispectrum, you have to take what's called a 6-point correlator. That will determine your variance, right? So there's 6 copies of the field. And it turns out that if you take, what people tend to do is they take Gaussian covariance, which means if you approximate this covariance, so you take let's say you take a 6-point function, you approximate that by Wick expansion into a product of 3 2-point functions. That's what's called Gaussian covariance. But in reality, you're measuring something that's already non-Gaussian. So you have to worry about this non-Gaussian covariance. And so what we show here is, and it's very hard to compute this analytically, but in this case, we used a very large number of simulations to get it from simulated data, so it's pure dark matter. And then we had an approximate form, analytical form of this covariance, and we show the ratio of your non-Gaussian covariance measurement FNL and your Gaussian measured FNL. And you see that depending on your value of your maximum resolution, your maximum K max in this case, so this is maximum momentum, you see that there's quite a large effect. And even though we cannot get these very high high resolution simulations at high redshift, at least we don't have them, we can use these analytical forms to predict how large this effect is. And we find that this is a huge effect for these local non-Gaussian, even at high redshift, which is remarkable because these modes are very linear, right? So these modes are almost as linear as a CMB, but we find that this is actually, if you neglect this additional covariance, you highly overestimate your constraining power. And you think, well, who cares? We're not going to measure this anytime soon. Does it have any real effect on anything we hope to measure soon? So as mentioned, in principle, you can also measure these radio waves, these 21 centimeter waves from at low redshift. And it's quite a nice property because it's very cheap. It is relatively cheap. Yeah, so if you want to do optical all the way up to redshift 5, it's expensive. And people, of course, are thinking about these kind of experiments. But radio, in principle, is relatively cheap. So we came up with this idea of building this very large array called the PUMA array, which I think is like 512 times 512 dishes. So it's a huge array. Didn't get a lot of support, unfortunately, but in principle, maybe yeah, at some point I have to look at it. And one of the key things that we predicted there, or the key reason why we thought this is a good idea, is that maybe we can get to this illustrious values of FNL. But in the forecast that people made for this original experiment paper, they did not include non-Gaussian covariance. And so we redid that forecast and showed that this can reduce your anticipated constraint by a factor of 5, right? And you have to imagine that might sound, okay, maybe it's not that much, but let's say I predict FNL of delta FNL of, I don't know, 2. Then a factor of 5 means you're back to pre-Planck eras, right? So it's really quite a big effect. And also to improve it, you need many more modes to get to that same value. So it's a big loss. So non-Gaussian covariance has a real effect, both at high redshift and at low redshift. Now, one thing that might help you is if you actually cross-correlate, but I will not talk about that for now. Something that we already found this to be an issue in the CMB. So even though the CMB is very linear, it's also lensed, and if the CMB is lensed, it also introduces this additional covariance. But when we showed that you can, if you de-lens, you can remove this. So then the question is, can we degravitate, right? So all this additional covariance comes from the fact that things are evolving due to gravity, and that introduces these nonlinearities, which introduces non-Gaussianities, and therefore non-Gaussian covariance. So you can do this. It's a long story by itself, and you can also do this analytically, but the question we came up with, can we do this with some modern AI techniques, okay? And so that's what we set out to do. We used a very large number of, well, actually only 48, but very large simulation boxes. So this is pure dark matter. So it's a pure dark matter simulation. And then this is what you put in. So this is at high redshift. This is kind of the pristine field. Again, we're trying to constrain inflation. You want to have the most pristine field possible. And so using these neural nets, we are able to reconstruct these initial conditions. So we can bring back that information that's lost. And to make that even more precise, to make this more quantitative, you can cross-correlate, computing the cross-correlation coefficients between the initial field and the initial field and the late time field and the reconstructed field and the initial field. And you find that correlation of 1 means that they're perfectly correlated. So as shown here in orange, you see that if you take this UNet, our detector that we use with 256 cubed particles, you get a correlation coefficient of about 0.9 at K of 0.5, right? So you're really reconstructing this field very well. That's also, if you look at directly at the power spectrum, that also works. Now, of course, what's the effect, of this? So here we have a nice spider plot. The spider plot shows you how well you can constrain all these cosmological parameters. So here you see your favorite NS and sigma 8, which is related to AS, and then all your non-Gaussianity parameters, right? That you have here. And this is in green if you do not reconstruct. Here, if you only look at reconstruction. But what's nice about these networks is that you can get the full covariance, so you can combine these data sets and you find improvements of about factor 3. So you're really getting information back from these gravitational interactions that kind of mix up information into these higher endpoint correlators. Yeah, so the idea is that nonlinearity moves this information to higher endpoint functions, such as gravity. So you start out with some almost Gaussian fields, but gravity then spreads out the information over all these higher endpoint functions, and these neural networks bring it back. You get improved parameter constraints, especially on non-Gaussianity. Now, of course, we're not observing dark matter. We're observing, say, galaxies in redshift space, and so you'd have to do the same trick for, in this case, we're using halos, but it also works. Okay, so just to show that this, in principle, could also be applied to real data as opposed to just imaginary dark matter fields. So my final, I guess, 10 minutes, I discuss what else we can do. So as said, so dark ages is promising, but very hard to observe. Even if you have some pristine measurements of these things, you still have information loss. You can bring it back with neural networks. What about this epoch here? So I'll let anyone else in large scale structure talk about this, but there's also this area in principle that has a lot of modes. And the question is, can we actually use those modes? Lots of volume, many modes. Are these useful? For astrophysics, so you have to imagine that whatever you observe there is highly astrophysically contaminated. It's, when the first stars turn on, they create all kinds of terrible stuff for cosmologists that we don't know how to deal with. And it's also very hard to model, right? So in principle, you really have to do kind of a heavy hydro simulation over many scales to capture this. And so we rely on these semi-numerical simulations, which kind of use inpainting together with perturbation theory. So what about cosmology? Can we use any of this information for cosmology? It turns out if we just look at the power spectrum, so the Gaussian part of this field, turns out there's very little constraining power. The question is, can machine learning help you the same way, right? We have some field, we know it looks very convoluted. Can we get back the initial information, which can be used for inference on inflationary models? And so that's what's shown here. We have some 21 centimeter field, some brightness temperature field. This is the initial field, and this is the predicted field. So we get an interesting, a nice reconstruction, again, showing that in principle, you can get cosmological information about these fields if you use these kind of techniques. And so we have analytical ways to bring this back in a dark matter field, and maybe even maybe like a galaxy field, but it's going to be very hard to do this analytically with something like 21 centimeters, simply because it's so astrophysics-y. Now, one thing is, if you ionize the universe, there will be a moment when you get these large areas where there's no signal. Yeah, it's just zero temperature. So then in your reconstruction, you also get these areas where there's no reconstruction. Yes, that would be pretty bad, which means again that your correlation coefficient will be affected quite a bit. But in principle, you can complement the measurements of 21 centimeter with some other line. Yeah, of course, there are other atomic lines you can use to measure this structure. And it turns out they're always, well, in many cases, they're anti-correlated with the 21 centimeter field. So if you use those, you can get back to a good reconstruction. So that's what we show here. So that's very nice. Now, of course, application of this, you have to add noise and whatnot and systematics to see if this will still works. But I think it's more a proof of principle that maybe we can use all these modes in some future, far future. Okay. Now, one final comment is that, okay, I'm talking about reconstruction here using machine learning, which means that we reconstruct and then infer our cosmological parameters. And many efforts are also there to directly infer. So you give me some observation and I'll tell you what is FNL, yeah, which would be also nice. And so another way of thinking about it, you can also go forward. We go backwards, you can also go forwards. Now, what I do like about this method is that I have some idea where this information is coming from. And this is always like machine learning, something that I have not worked on for a very long time, maybe 2-3 years. But it's very black box. It's very black box nature. And so you don't know where the information is coming from. In my mind, if I give you like some big piece of data and you tell me, oh, NS is 0.6. And like, well, how does it know? Well, my machine learning network tells me that's the case, right? So, and that's, I don't like, but here I have some idea, oh, this reconstruction I understand because there is a coupling between small and large scales, and it's just using that. I can even use some analytical methods to get the same result. So I know that this is not completely made up. Now, all things considered, you should probably try many different things and see which one works best and which is most reliable. So what can possibly go wrong? Yeah, so I'm ending this with maybe just a warning. What can possibly go wrong? So we try to do this. So we want to learn about inflation. We say at some point, FNL, we know how to measure this. We have optimal estimators, but they're computationally not very cheap. Yeah? So if you want to do this, let's say for higher endpoint functions, want to measure tri-spectrum or even beyond, it's really hard computationally. So maybe machine learning could help with that. So as a kind of a first, you don't want to start with the 5-point function. So you start with the 3-point function because you know how to do it. Now we did this and we find that we tried it on both on the sphere and on flat skies. On the sphere, it turns out to be pretty challenging, but we're making some steady progress there. The main conclusion so far are that just doing the sphere is challenging and it's resolution limited. So even with, I think, if we're optimistic with the current architecture that we have, but we actually today we made some improvements. We might get to resolutions that are WMAP, as a pre-planning. We might be able to do it on WMAP, but okay. Maybe in the future we can do it higher. Usually it's a GPU thing, it's a GPU memory thing. The architecture matters a lot, so really it's a lot of fine tuning. So we try a lot of different things. You cannot use like a network out of the box; it will just not work very well. What we find is that making optimal errors based on existing methods are reached when you have about 450 training maps there. Okay, so the main conclusions, I would say that inflation is the most likely scenario. Of course, as a Bayesian inference is the most likely model at the moment. It does not only explain these old observations, but also the new ones. So the fact that we observe a scale invariant power spectrum, we observe this phase coherence on large scales. That is something that inflation predicts, right? So that's nice, given the constraint that it solves these background problems. At the Gaussian level, it's kind of limited what we can infer. We can only infer AS, NS, and hopefully tensors are, but that of course depends on whether they are there or not. And I think non-Gaussianity in that sense could be pivotal, right? They really add one additional way to constrain these models, and they are much more flexible. So there's many ways to fit for the data. Now, to reach these thresholds, the universe is just really Gaussian. And if I look at the CMB, yeah, it looks very Gaussian. So that means if we want to measure these very small effects, which they seem to be small effects, then we have to measure every single mode that's available in the universe. The main point of adding machine learning is that in principle, that allows you to have some way to bring all this information back. So whatever is convoluted by gravitational evolution or astrophysical evolution can be brought back by these machine learning methods. But of course, we should remain cautious and use common sense. So how machine learning will play a role as my final statement, I don't know. I think it will play some role, but we'll have to remain cautious, and we'll see if it actually brings us closer to deciding what model of the universe really happened. That's it.